Okay, so like I promised last week, today I'm going to develop that language that allows us to describe how these holomorphic extensions behave, to some degree, of course. So I apologize in advance if it gets just a little bit technical. I try not to be too technical, but yeah, we'll see how far we get. Agenda. So, right, what we did last time, we showed some basic elementary functions and how they extend to functions from L to L. Right, and so L has the advantage of unwinding the periodicity of X. So we have actually injective holomorphic continuations for those functions that we looked at. But we also saw the holomorphic continuation of, say, a translation. And that doesn't quite behave as well. We'll see a bit more today in what sense and how to account for it later on. Okay, so in order to describe how these maps behave or what they do when they map certain things to certain things, right? We have to introduce what we call a real domain. So set U, the Riemann surface log, is called a real domain. If well, on the board they look kind of like those standard quadratic domains, but of course in a totally different chart. So if there exists a continuous real function f on some interval from a to infinity, where a is bigger than 0, yeah, positive value. Okay, such that U is the set that I'll denote by UF. That's the set of all points on the Riemann surface whose modulus is greater than A and whose argument is less than F of the modulus. Okay, so these are domains, right? Remember, Riemann surface is a half plane, right? So these domains, here's my A, right? Here's my continuous function. It could be something like what we had seen before. And then it's mirrored on the other side. And so here is a argument equal to 0. So it's some kind of domain like this. But it also includes, say, right, in the Riemann surface, the standard quadratic domains, they're bounded, right, in angle. So those are also okay. Right? The F can go to 0, doesn't have to go to infinity. In fact, you definitely will need all of those. Describe things. So examples, right? So I want to introduce a slight generalization, although I'm not using that today, to standard quadratic domains called standard power domains. Those are examples, and those are examples that might look like this in the Riemann surface. So for epsilon between 0 and 1, that will be the power. For quadratic domains, that was 1/2. And for some constant c greater than 0, we can look at set U. What do I have to see in vertical? This is the epsilon. So how did I define this? Ah, right. So this is going to be the inverse, the pullback, we are pi 0. Remember, pi 0, pi is the covering map for the Riemann surface. Pi 0 is the restriction of the covering map to the sector between minus pi and pi. That's injective, so we have an inverse to that. The lifting of pi 0 inverse of complex domain omega c epsilon. Complex domain is defined just like standard quadratic domains. Omega c epsilon, that's the image under phi c epsilon of the half plane. Pi c greater than 0. Right. Where phi c epsilon of c c plus 1 plus c to the power epsilon. Okay, so when epsilon was 1/2, we get the standard quadratic domains from last week, even the week before. So these are the picture looks the same as far as I'm concerned. But on Wednesday, I will need these particular epsilons. They're not just 1/2. You know, we won't be able to do, but that's just an example. And in fact, so these are somewhat special because they're liftings of domains on the original logarithmic chart on the complex numbers, like the standard quadratic domains. Yes? Thanks. That's how. Same as for standard quadratic. Okay. So C just tells you for the left, but the leftmost point is on the real line. Yeah, so what am I going to say? Oh, right, there are other real domains. No, they are not a counterexample, not the example. The right half planes on the Riemann surface are not real domains. They don't have boundary function in the argument as a function of the modules. All right. Yeah, I thought that it might be good to point that out. Okay. And so remember that the Riemann surface is actually a definable manifold, right, in Rnx. And you can check that UF is definable in that on that manifold, if and only if F is. Okay. So if you're interested in also checking definable such domains, and I will actually use definable domains to track the behavior of extensions. So what else? Well, these real domains, right? They're all simply connected. And they have, they're symmetric with respect to the x-axis, and things like that. Right? These might be properties that I'll use without mentioning. They're very nice domains in that sense. Okay. They're also split, right? If you want, the real axis separates any such domain. Complement as two components, positive angles and the negative angles, arguments. Okay, and so these standard power domains, I want to single them out a little bit, right? So they actually are liftings via pi 0 inverse of domains in the original logarithmic chart on the complex plane that are themselves they look themselves like this in that chart, right? So I want to single those out as a special class. So a strictly real domain is a set on the Riemann surface such that like these guys here. So U is the pullback. We have pi 0 or something else. Omega f. Where f again from 0 from a to infinity. Real continuous map. And omega f set now back in down in the complex plane. The logarithm chart is a set of all z such that the real part of z is greater than a, and the imaginary part in absolute value is less than f of the real part. And so, like the standard quadratic domains, where f is, or then the power domains, right? These guys here, their liftings are called strictly real domains. Does that make sense? So, in the Riemann surface logarithms, as strictly real domains, all length is strict. Argument between negative pi and pi. That's what happens in this case. Any questions so far?
Can you explicitly indicate how the function f becomes the function there, or maybe you don't want to do that?
No, I don't want to do that. It's an exercise.
Okay, fine.
But I will do stuff like that today. I'll formulate a couple of exercises along those lines. Not between this chart, the original chart, and L, but between L and its log chart.
But if that f is definable, is then the lifted f, so to speak?
Yes, because pi 0, right? The restriction of pi to that string is definable.
Okay.
That only needs restricted exponentiation. That's right. Okay, so right, as a warm-up, coming back to those examples that we discussed last week, we can now give a bit of a description of what happens, what these extensions of what is a scalar multiplication or powers or x per log do to domains like that. Okay, as a starting point. So scalar multiplication, you know, that's pi r for some constant r, so r greater than 0, or the r's power function, any one of those. So the holomorphic continuation of the Riemann surface of these functions, PR and MR, are, right? What do? Well, they map real domains to real domains. It's easy to check. Okay, so and if they are definable, they stay definable.
And onto.
Yeah. Oh, yeah. Two. So onto. Okay. Of course, injected. Right. So that's not hard to check. Then what about log? Right. So we had this extension of log to the Riemann surface that we call log bar, which again, if you remember, in the log chart, we have the standard branch of the logarithm, which lifts up to a map from L to L. Okay, well, almost L, except you have to omit the segment on the real line between 0 and 1. Okay. But I'm really only interested in that, say, on the right half plane where the modulus is greater than 1. It's perfectly fine. Okay, so this log bar, what does it do? It maps, in fact, almost the same, maps real domains to real domains, but there is an extra to it. It maps real domains onto strictly real domains. Right, so the log crushes these big domains up there into domains where the angle is bounded. Quite severely bounded. But it does also map definable things to definable things. Okay. So, you know, X of course does the exact opposite, so that's okay too. X bar maps definable, strictly real domains. X bar only extends to the strip. That is the image of the log. Okay. Strictly real domains onto real domains. X can really blow things up. Okay. So that, that's very promising because those are the, right, again, those are kind of our right? Those are the building blocks for our terms, except for addition. We don't have addition. And so when you do it, right, we can do addition and even translation, which is a very limited addition, right? It does not have, well, behavior like this, right? So TA bar, we saw that, does not map definable, definable real domains to definable real domains. Doesn't even map them to real domains in general. Because it, right, once you have, what does it do? If I look at an image, this under translation, does that look like in general? So, well, it will be a domain where the boundary now oscillates. Oh, okay, I'm not. This is not accurate. I'm not telling any claim for accuracy, but I think you get the idea, right? So the image might look like this, which is not a real domain because the boundary here is not the graph of a function. Yeah, there's wiggles in it. And so we will have to somehow account for that. So there's no nice statement like this that it's valid for translation, even by positive real number. All right. Okay, one thing that we can say about it is if we have an angle bounded, so angle bounded just means it's between minus c and c for some positive c, like the argument on the set. If you take an angle bounded domain, take its image down here, then it's still definable, right? Because we have only finitely many wiggles. We only need restricted sign to do that, to define the image. It's only for the things that are really big, where nothing stays definable. It's TA.
You don't suppose it has to be increasing, right?
No, I'm not. No. Well, we'll be looking at a lot of f going to 0, in fact. Okay, because when I take the log of something like this, I get something where the argument is bounded, so something I call angle bounded, so like a standard quadratic domain. And then you apply log again, you get something where the boundary function already goes to 0. Okay. So yeah, we can avoid those now if you want to actually describe behavior of other functions. All right. So, okay, we need to develop a bit more language here. And we'll keep the lemma in mind, but we'll look at these functions first to see how much we can actually say for these kinds of functions anyway. For the basic elementary functions, and let's say they're compositions. Which is already a nice collection of functions. So when we look at definable real domains, as long as I just look at the terms at infinity on the logarithm, Riemann surface, the logarithm. When I talk about terms of sets on the Riemann surface, I mean the terms as the modulus goes to infinity. Okay, so when you think about these real domains just as terms at infinity, right? They correspond exactly to terms for the definable ones. They correspond to terms of functions in our Hardy field. Okay, so every term f, positive anyways, okay, in our Hardy field, that H is the Hardy field of R and X still. Okay. This corresponds to a unique term at modulus of x equal to infinity. So you can figure out how to define terms of sets like that. It's only really one way I can think of it. It's the unique term at infinity in L of a definable. Okay, make sense? Do I have to explain that? So terms equivalence classes of sets, right? That means when you intersect them with a sufficiently far out right half plane, they agree. So that introduces an equivalence class in all real domains. And you look at that. That's a germ. All right. So now with this identification in mind, so now I have terms of definable real domains correspond exactly to terms of functions in H, positive functions in H. Okay. So under this identification, we're going to look at the set of all strictly real definable domains. Okay. So that's all F. So that UF is actually strictly real.
I ask one thing about these real domains. In this picture, the suggestion is that F goes to 0 as Z goes to A. I mean that. Or that.
Yeah.
Is that so? Is that?
It doesn't have to be. So if right again, because we're really only interested in the terms, you can always make it that way.
That's why I'm asking it.
Right. So I'm drawing it like this because if it's not right, if it starts somewhere here, then I just cut it off.
Yeah. Okay.
So, but I'm not interested in that part anyway. So I'm only interested in the germs. So I didn't specify that. But sure, yes, that's true. Right? So whether we have to cut it off like that or not depends on it. Okay, so this H here, right? This HSR, this is a subset of the Hardy field, and in fact, it is downward closed. Downward closed. Subset, not of the whole Hardy field, but of H positive. It's not an interval, doesn't have an endpoint in the Hardy field, but it's downward closed in the Hardy field. Okay, does that make sense? Any f that's smaller than some other f that's already corresponding to a strictly real thing must also be strictly real. So it defines a cut, H positive, so to speak. Okay. So that means, right, we can specify a bit more about what this lemma over there is actually saying. Right? The lemma says that each one of these extensions map definable real domains to definable real domains. And in fact, right, since it's injective and so on, we specify a bit more, right, for terms infinity of real domains, or sorry, of definable real domains. The following happens. For every r greater than 0, there are functions, one for the scalar multiplication and one for the power function. There are functions which I'm going to call new PR, so new sub whatever that function was that I extended, and new MR. So these are now functions from the positive elements of the Hardy field into itself. Not saying anything about definable. These functions are not, as far as I know, definable. But there are functions such that if I take the image under MR of some definable real domain, again, not a definable real domain, right? So this is going to be the definable real domain, new MR of F. That's how I define this function, new MR. Okay. For and same with the power functions. PR bar of F equal to U PR. Okay. Make sense? That's just what this is saying here right now. And you can, for example, right, this function will have to be increasing. Right. On bigger domains, you will have a bigger image. So that's okay. So we can do something similar with log. Same function for log. And one for x. Whereas for the first two there, right, the domain of this function u is the whole positive part of the Hardy field. Well, for log it is 2, same thing, right? Because any definable real domain lives in half, so log is well defined as long as we stay away from 1. Those terms make sense. So 2. Right, function log H positive, and the image is in HSR. Images of definable real domains are definable strictly real log, such that log bar of UF is equal to U. Okay. And again, this is increasing, that's for sure. But the image in this case is not all of H positive. And then you have the inverse for x, right? There's a new x of HSR into H positive. Right, so we have a bit more of a description here.
Is this the inverse of the one and
That's
two?
correct. Right, yeah. So let me add that, touch that. New log proposed with new x, or the other way around, is the identity on whatever domain of the one. Okay. So in this case, it's the identity on HSR, right? For the log, it's the identity on.
Can you somehow describe this cut, this guided closed subset in a sort of concrete way?
HSR cut? Well,
Yeah.
again, so like the H under, those are all things that are contained in this strip,
All right. Yeah.
right? And they're not
Right.
the ones with the constant functions, so they have to be domains like that.
Yeah. But
right. But where exactly it cuts off is very hard. No, I can't describe exactly where it is.
I mean, in terms of R and X.
Right, yeah.
Okay.
No, it's.
Oh, I see.
I don't have a precise description in terms of just say.
Because there are some standard cuts in.
Yeah.
In the party field. Anyway.
Right. So I don't know if it corresponds to any of the standard cuts that you guys already know. Not sure. I mean, it's just below the term of 1/2 somehow.
Below what?
The term of 1/2. So sorry, a pi over 2. Like the constant function pi over 2. But how far below, I don't know exactly. Okay, so all these functions, the new functions here, they're order preserving bijections. Okay, so and we can extend this a little bit, right, to certain types of functions. All the things here that are composing the three. Right. I do want to say that helps us figure out a way to describe what happens with the other terms that are not quite so. They involve translations, for example. So if we look at E, so that's just a set of all these predicates that we looked at in this lemma, right? So that's log x together with all multiplication by r symbols together with, well, these are not really predicates because they're predicate. Sure. These are the basic ones we know how to deal with right now. So if I look at this set, right, and I look at all finite compositions of elements in there, so finite compositions. Every finite composition, well, because yes, so another lemma. But if you compose, say, MR with PS, then what's the image under that composition? That will correspond to the corresponding composition of new MR and new PS. Okay, so these are really quite elementary, but so any of the basic words, right? Well, all the basic words, well, you know exactly what their domains are, but I'm going to describe it a little more vaguely, and all sufficiently small germs H. Okay. You're going to see that mu g of H, okay, that's still going to be in the domain function F, because those domains are downward closed in H positive. Okay. So we have this, and in that case, what this means, I can apply F bar to G bar of UH. That makes sense. And that's exactly the final real domain defined by F composed with G evaluated. Okay, so composing two of these words, extending, taking the image is the same thing as composing these two functions and applying that term. Does that make sense?
Do you want FG to be E in E circle or just in E?
Where?
In the statement of the
No,
letter.
this, at the moment it's just in E, right?
Oh, okay.
And then we get a corollary from that for E circle.
Oh,
Against
okay.
each other. Next, right? Sorry, maybe I'm going a bit slow. I kind of need all of that stuff just to make up the right language for later. So for, yes, any of the compositional words came from E, right, there exists a downwards closed set, but there exist two downwards closed sets. One of F, H2 of F. It's positive elements. And an order preserving projection. You have H1 and H2 of F. Okay. Which does the same thing to these words, right? So in other words, F bar applied to UH is going to be the new F. U is a new F of H. Every H in H1 of F. And these guys behave well under composition. So these are all functions on the right of zero in the Hardy field as germs. If I look at them as germs, I'm going to say always about the raining. So as germs, 0 plus H positive. U F composed to G is equal to F. So that checks. Of course, yeah, you prove both of these together, right? Okay, so it makes sense. Yeah, I don't think the math behind this is very tricky, but this is what we really use as a language. So, and this corollary, right, it just does not work for the translation. There's not going to be such a map on the definable real domains or on H positive, because they don't map definable real domains to definable real domains. Okay. So the question is, how do we somehow weaken this corollary? And this is very informative in some sense. So that we can find a statement that applies to all germs, not just the words in E0. Okay, so in order to extend something like this to all germs, I need some standard additional notation, right? The squiggly I, that's the set of all infinitely increasing terms in H. Okay? So infinitely increasing, those are just the terms that go to infinity. Set of all infinitely increasing right, that's an upward closed subset. That is certainly a very standard cut in H. I'm also going to occasionally use the set, the complement of I, right? So called B for bounded terms. So that's H positive minus I. And I'm going to look at D, which are the terms going to 0. Okay, so these are all the 1 over F's, where F is an I. That's a downward closed subset of H positive. Make sense? Aha, so what we need in order to weaken this really quite strong statement for all words in E0, I need something called level. And I think we mentioned it briefly last time, and people asked if I could define it, and yes, I'm going to define it now. So remember, for our definable terms, we have one notion of exponential height, which is a syntactic notion based on terms defining that term. Okay, but there is also a quite similar measure of size for these germs that is purely defined in terms of germs of functions. So Rosenlicht, I think, was he the one who introduced this level?
It's time I ever saw the word.
Yeah, probably in Rosenlicht. Right. So this is just about any germ and infinity of real functions, right? So an infinitely increasing term plus infinity F said to have level if the following exists: if there exist two integers k and l such that if you take a germ f and you slow it down on the left with a certain iterate of log, namely in this case the lth iterate log, okay, this thing becomes equivalent to some other finite iterate of just log, namely log L minus k. When this happens, we say that it has level. So in this case, the which one? The k is unique. That needs to be checked, of course. Is unique, and it's called the level of f. The L is not unique because once you have this for an L, you can compose with log more on the left, right, on both sides, and the relation still stays true. So there's just a minimum L, right? But this happens first, if it does happen at all. Make sense? So for Rnx, right, there is this theorem by Chris and Dave. They studied levels in Rnx. Among other things, they showed that every germ in our Hardy field, or every germ in I up there, is leveled. Oh, I guess marker alphabetically comes before Miller. You were sitting here, so. So fact, right? Every F in I has level. Okay. So I'm going to use that. In fact, I'm going to extend, right? I'm going to extend level in the obvious ways to everything on H positive. Which again says the obvious way. So it's already defined on I. On D, we just define it to be, right, for F and D. We're just going to set the level F to the level of 1 over F. And then if we have anything that's bounded but not in D, set the level to minus infinity. Okay. So if you do that, so there's right, those two guys, they prove a few things about level in Rnx, and that extends now to this definition here in the following way. So this is nothing new really, it's just translation of their propositions. I still and them as far as I'm concerned. Okay. So take two terms in H positive. Right, so there's a couple of things. On the infinitely increasing germs, the level is an increasing function. Okay, so F, G, and I. F less than or equal to G implies level F. G. Right, so that's already something that's different from EH. This is not true for EH. The syntactic complexity does not behave that nicely. The second, F and G are bounded both. And F is less than or equal to G, well, then it goes the other way. Well, that's just kind of by the definition. Right? So it follows from one, the definition, that here we get the level of F. So functions going to 0, faster they go to 0, the higher the limit. And then there are a couple of things like under composition, level is very well behaved. So if G is infinitely increasing, right, and F is anything. Okay. Yeah, okay, so if G is actually infinitely increasing, I can plug it into F. So then the level of the composition again, Chris and Dave proved this for infinitely increasing germs, and with this definition you can translate it to this, and that's why we chose minus infinity for the bounded ones.
Excuse me, Patrick.
Okay.
Excuse me, Patrick.
There's behavior under multiplication. That's for any two F and G's, right? The level of F times G is always less than or equal to the maximum of the levels. this remains true when we extend the definition.
Excuse me, Patrick.
Yes.
No, yeah, maybe in two, F and G are in D.
No,
Maybe in two.
no.
I don't know. Bounded, just bounded, not going to zero. Not necessarily.
Yeah, because like for the bounded ones that don't go to zero, the level is minus infinity by definition.
Yeah. Okay.
It's always less
It
than
is
one.
yeah, it is included. Yeah. Okay.
Yep, it is.
Yeah. Thank you. Sorry.
Okay.
Yeah.
Okay, and in 4 you have equality at F and G.
That's right, yes,
Yeah.
that's exactly right. With equality if they're not the same. Level of F is different. These are basic properties of level.
I would. I thought if it's probably also true that if F and G are both in I,
Yes.
it's also okay.
Oh yeah, right. Especially, right. There's no restriction on F and G in this 4.
Right.
And just for our purposes, right? So we have now level and we have exponential height, and they're not the same, right? Because as we might remember, this one is not true for exponential height. So counterexample of that. And of course, also 1 is not true for exponential height. So the best we can do in general is leave that as an exercise, right? For infinitely increasing terms, we can say that the level of F that's always equal to the exponential height of the leading monomial of F. Okay, so leading monomial is the thing that comes out of our construction. Okay, so this is the leading monomial. Okay. Okay. And that's because for leading monomials, exponential height and level are the same. Okay. So it's equal to the exponential height of the leading monomial, and that's always less than or equal to the exponential height. Okay. So there is an inequality that always holds for level with respect to exponential height. Okay. But I leave that as an exercise. Obviously, you have to prove this somehow by calculation. Terms. Okay, let's take a 5-minute break. Then I'll use this to introduce the language that we can describe behavior of all terms in theory stage. Thanks.
Yeah, so that. No, I know.
Are you doing a red eye? Saturday. Sunday morning? or
No, it's
Saturday?
that's more like, I don't know, Saturday afternoon. Thought it was impossible.
I had a really terrible time when you were.
Good for the-
No, I don't see one.
0 ones.
This place always
One
better.
Even level
over.
zero?
I'm saying point where you. Double points. And It's one over absolute value that's minus C where C is. That
No,
So
that doesn't
just
make
don't
sense
need it.
here because I want something. I remember that even one application of law gets you into the constant, right below constant things. And another application of law gets you into D. So there's not much happening. My point of view, for the functions, the unit. So, no, I don't need somehow distinguishing. What happens?
no, you just below, but still in half.
Or pirate too.
Architecture.
Yes, and that. Exactly. Absolutely.
You know, we have some.
Well, okay, yes.
Okay.
I don't know if. Just start again. So it's still out. Okay. And microphone is good. Thanks. Okay, so right now I'm going to look at how does the level of f compare with the level of nu of f for various nu. Okay, so as an example of an easy case, if w is one of the power functions or the scalar multiplication functions, then the level doesn't change. The level of u w of f is equal to the level of. Okay. So of course this does involve a little bit of computation. Right. So maybe I could make this an exercise. but it's not too surprising. Like for example, when you have a real domain like I was drawing there, where the angle is unbounded, applying this kind to it still leaves it unbounded. But it's even more precise. Right now, what really interests me, right, is new log. That's the key to everything. Okay? So comparing new log f, the level of f, the level of new log of f, that's the key point. And if we start, oh, yeah, no, okay. We start with a term that's in d times log, right? So that's the product of a term going to 0 with log. So it doesn't necessarily go to 0, maybe it can go to 4. Okay. For such a term, another term, final term u, which is a unit in the sense that u is equivalent to 1. Quotient, right? So the limit of u is u of x is x goes to infinity is 1. There's a unit such that this happens, and new log of f is equivalent to f over log composed with e to the power x times u. Okay. So this is the computational part. Doing this. So I think I do need to explain this. This is kind of a key point. All right, so for that, right, I really have to describe how do we compute new log of f. So new log of f is the term of the function which takes as input modulus and spits out an argument, right? The bounding argument for the domain. So the way you compute this is the following, right? So we need two auxiliary functions, rho of f, which I'm just going to call rho. Okay, unless I need to really need f when I don't. So that's going to be the square root of log square plus f squared. Okay, that kind of represents the new modulus. And theta, which is going to be theta of f, which is the arctangent of f divided by log. And f divided by log goes to 0 by our assumption. So that. And so then here, like this is the little geometry / computational exercise, show that new log of f is equal to theta of f composed with rho of f inverse. So this is here, I will actually show the rho of f also goes. Okay. So to do this, right, again, work in the log term. Right? Otherwise. So that's the one on the left that I had on the left last time, lower left. Log chart for the Riemann sequence. Okay. Now, assuming that exercise, I'm going to give you a sketch of the proof dilemma. It's not.
Sorry, what is the subscript for the new there? New there? New
Oh, log.
Oh, log.
Yeah. Okay. This is just, you know, one of those Hardy field calculations that you see. Once you know this, It's just Hardy field calculations, so pretty simple ones. All right. Right, we have f over log is in D, so it goes to 0. Okay. And of course we know how arctangent behaves. Near 0. So that's really just identity plus something small. Okay. Which means theta is equivalent to f over g. Period. And it also means that rho
Over what?
f over log. F over log. Okay. Right, because arctangent for small arguments is like okay. And rho, on the other hand, is of course, because f goes to 0, right, is now equivalent to log. Okay, but then you have to be, right, you have to use that. What does it mean to be equivalent? We write that out. It means there exists some term v, which is a unit. Is equivalent to 1. Okay. And now I can write rho equal to log times. So now we're not talking equivalences, we're talking equality. Okay, so now you, for example, composed by rho inverse, because rho goes to infinity, that means I get x is equal to log composed with rho inverse times v composed with rho inverse.
Rho inverse here is the compositional inverse? or-
Yes, compositional inverse. Okay. So that's why I find x on this side.
That's what?
That's why I find x on the left after composing with rho inverse. Okay, so this is still a unit. That's going to be my u. Okay, and yeah, now just unpack it. It's still an equality. This is a unit. Oh, sorry. This is not here. Did I do? I composed with. Oh, no, it is. Yeah, sorry. Yes. Okay. So if you unravel this now, you get e to the x times u equal to rho inverse. Okay. Now let's see if we can plug this in to finish, right? The other problems that we have there and our exercise, and I'm just so the exercise that I just placed. You get new log f equal to theta composed with rho inverse. Yes, that's from the exercise. That's equivalent to f over log by the first equivalence there, composed with rho inverse.
I suppose e to the power of xu should be e to the power of xu inverse. It's 1 over u.
Yeah.
Since you bring
Oh,
u to the
okay. 1 over u is also u. Sorry.
Yeah.
Yes.
Doesn't make
Let's
it
call
that.
this one 1 over.
Oh, okay.
Yes, you're right. 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 So here, right, plugging something in on the right keeps the equivalence, and we have f over log composed with e to the x2, which is 10. Okay. So it's not right. It's kind of what you get from these definitions and from the calculation. How new log calculate. Okay, so that means that new log, right? It gives us a way to well, weaken the statement that we have for new log, which is that it's this new log is this increasing map, right? That maps the initial segment to actually the whole thing to the initial segment, h and star. So we get something a little weaker, but that's more informative when we try to extend other terms. For a term f, positive term f, we have that the level of new log of f is going to be equal to, so level of this thing, which is the sum of the two levels. The first one is a product of f with 1 over log. Okay, so it's going to be the level of f divided by log plus 1 if f is d times log. D times log is again a downward closed subset, a cut. Right? And otherwise, it's always going to be minus infinity. Because in that case, it's a unit. Why can we see that? That's actually obvious, doesn't it? We just put proof here, right? So if f is actually bigger than d times log, that means when you divide f by log, you don't go to 0. But you must be going towards at least a constant, possibly infinity. Okay. In that case, right, the arctangent of f over log, in other words, goes to a constant. It is a dominance equivalent to 1. Not equivalent, but dominance equivalent. Which means that new log of f is also dominance equivalent to this case. Okay. So it has a minus infinity. Yeah. That makes sense? Right, so new log collapses all big definable real domain into the biggest ones into something of level minus infinity, so units, so to speak. And then starting with anything in d times log, which still contains something like square root log. Okay. It will start sending it to stuff where you have an integer length. According to that. Okay, so now I think we are ready. Oh no. Now we're pretty much ready to find kind of weakening that we need. Like we can eventually prove for all terms. So first of all, like the levels, they partition D. So I'm going to use that partition first. So for A and Z, we have two things, right? EK. Those are all terms going to 0, level of K. Of course, a partition, right? And then also we have E greater than or equal to K. those are downward closed segment cups. It's greater than level. For those going to zero, the bigger level means going to zero. And I also want to define J to be whole positive collection minus this weird set d greater than or equal to -1 multiplied by log. See the second part. So d greater than or equal to 1. All the things going to 0 with level at least -1. So say anything like 1 over log or go to 0 faster. But multiplied by log. Still something like that. So again, there's a couple of exercises related to this stuff. All things you should do in your own time. So if you look at d-1, right, that's actually contained in d-1 times log. And other thing that I'm going to use is that d0 does not intersect d-1 times log. In other words, H positive is partitioned into this guy, and then d greater than or equal to 0. Okay, that's a partition. So this guy here is somewhere in the middle. Make a picture. It's not like I can actually draw it.
Sorry, what are you partitioning?
H positive, the whole hierarchy of positive elements,
Yes.
is partitioned into this J, into that, and into D greater than or equal to 0.
Oh, okay.
Okay. And what we now want to do, based on what we have observed before on this corollary, we know that J gets mapped by D log into E-1 times log. Right, so this gets mapped into that one, not onto, but into an initial segment. And E-1 times log gets mapped into D0. Onto. Finally, 4, right? U log maps any dk where k is greater than or equal to 0 to dk plus 1. But that's all based on this code. Right, so new log makes a big crunch at the beginning. Right? All these things in J get mapped into quite a bit smaller one. This guy here. That one gets mapped into D0, even onto it. Then D0 gets mapped into D1, D1. So based on that, find the crucial describing what happens to all the terms. To call the angular level definition. Angular level. L is defined for all positive terms, okay, and takes values -1, 0, 1, 2. So not quite all integer values, only regenerated 1. Find Yeah, if maximum of -1 at the level of u log. Okay. So that's exactly that reflects the picture I just described. That's what new log actually does. Terms, right? So the picture I described can now be stated as a corollary. So this AL is decreasing. Okay. And for any germ F, positive germ, we get that for power functions and scalar multiplications don't change this angular level. R greater than 0, AL of new PR of it, AL of it. It's also AL of M of it. So we already knew level was preserved by those, so that doesn't change here. New log increases the level by 1. So it's equal to AL of F plus 1 based on the definition of the corollary. And correspondingly, right, exponentiation decreases. Right. About exponentiation applies to terms in HS strictly real. Those general level of mu x equal to AL of F. And things in HSR have angular level with these two. Okay. So now I want to use this angular level to capture how the other terms behave. Right? They're not as precise as what we had for the words in E0. Like translations don't do things, but just to explain a bit what translations do. Okay. So if this is the image, say, of some domain like up there under translation. Okay. But the general behavior of this boundary is still the same. What I mean by this is that there is actually another one, definable real domain. Well, there are two of them. One that contains the full boundary, and one that does not contain any points of the boundary. So the image under the translation is between two very similar definable real domains. And in fact, very similar here, it can be stated as having the same angular level. Okay. So translations, right? Okay, they don't even send things to definable domains or anything like that, but they take things that are framed by definable domains that's of the same angular level, to things that are framed by definable domains of the same angular level. So I want to make that definition what I mean by framed. Right? It's kind of that picture over there. Okay, so definition. So take lambda an integer. U and V, two subsets of domains, right? L and phi a function from U to V. Quite general, this definition, but based on what I just said here, right, this definition is the weakening that we need. So we call U a K domain if it's framed between two definable real domains of angular level K. Okay, so if there exists terms F and G, O is positive of angular level equal to K, okay, make sense? Such that U is contained in UG and contains UF. Like the picture over there. Okay. And we're going to say that the map phi is, right, this is now a map from L to L, so to speak, not a real function. So phi has angular level A. No, sorry, angular level lambda. If U is an L domain for some L, and I have to make sure the L is not too small, so it has to be at least -1. L domains are only defined for integers greater than -1. And what happens? For any K, right, so now this is kind of mimicking what's happening to this picture over there under translation. For any K greater than or equal to, again, this has to be so that it makes sense what I'm going to say next, because K domains are only defined for K greater than 1. So K greater than or equal to lambda minus 1 and L, or L, right? No, and L, and every K domain U prime contained in U, the image phi of U is a K minus lambda domain. Right, so the angular level lambda shrinks or explodes K domains to K minus lambda domains. Lambda is negative, then that means it explodes like X. Lambda is positive, it shrinks like log. So in the case of X, this guy here would be 1, for log it would be -1. No. For log it's 1 and for X it's negative. Okay, so like the scalar multiplications and power functions, they have their extensions have angular level 0. They don't change angular level. The map K domains to K domains, or appropriate K. Translation also has angular level 0. So the extension of translation on L has angular level 0. So that makes no sense. And then any word, so yes, U prime. Yes. Okay. Correct. Right, and then if we look at the words in E0, right, they are very precise. They map, and for them, the angular level is exactly equal to their level as a real germ. Okay, so that's just, that now just falls out from the way we looked at it before. Okay, so the words in E0 all have angular level equal to the level. Well, no, not the level, because if the level is negative, right? That wouldn't make sense. So maybe I should state that. And so I'm just trying to describe how the statement for these words in E0 weakens when we just use this. Okay, so for W in E0, Oh no, yeah, right. Sorry, yeah, it was right what I said. W has angular level, which is equal to the level. Yeah, the angular level can be any positive or negative integer. Okay. But the other thing that we have from before, right, is that for these words, EH and level is the same. Because these words are very elementary, right? So you can check that easily. And if I consider eta, which is the maximum of EH, W, and 0, right, then what we have proved for them is that W bar is injective. And holomorphic. Some eta minus 1 domain. That's just a translation of what we proved before. Right, so if eta is log, right, then the level is -1. So eta is 0, but the extension of log goes to -1 domains, to all real domains. Okay, so that's one of those examples. So you can just check this is true for all words in E0. This kind of statement, and it's this kind of statement which is actually true for all German. This is a weakening of what we proved for the words in E0 that can now be proved, well, almost for all germs H positive. Theorem. Continuation theorem. Yes. So if you have an infinitely increasing germ, sorry, for all infinite. Take one of those, and again, let eta be the maximum of 0 and EH. Okay. Okay. And lambda will be there. And then you can find two domains, right? There exists an eta minus 1 domain, like here. There exists, and right, and if it has level lambda, then the images will have a minus lambda in there, right? And a eta minus lambda minus 1 domain. E. And I holomorphic map. F bar B of angular level in the complex sense, like over there, equal to lambda, such that F bar restricted to reals is it. In the sense of the angles. So every definable germ has an extension like this. So in other words, the size of the domain that it extends to in this way is determined by its EH, right? this eta here. The way it collapses or expands domains is determined by angular depth, which is the level of F. It's a real term. So yeah, that's the see. Yeah, I have a couple of minutes. So, right. So this says something about at least every infinitely increasing term. So if you have another term, right, you can translate. If it goes to 0, then 1 over F is infinitely increasing. Apply this, and the level is the same. And so it still works essentially. But of course, not everything. Like the image of 1 over such a thing is not going to be such a domain because it goes to 0, not to. So it's not right. That's why I only state this here for the infinite. So yeah, I won't prove it because actually for the proof of this to go through the whole induction, you need to add a few more precisions, which I don't talk about. I mentioned some of that to Wednesday, so I have to. But there is partial converse to this. So I won't be able to prove it, but I want to state it. This partial converse follows from the uniqueness principle that I did prove first, second lecture. Right? So the converse says the following. Right? Take any germ that's infinitely increasing, and any eta, natural number, right? Not an integer, just natural number, and assume F does have a holomorphic continuation F bar on some U with values in a half plane on L, strict half plane on L. So where, in other words, U is an eta minus 1 domain and A is strictly positive. Right, so that's kind of the inverse. Here we concluded if from the EH of F I get this eta, that tells me how far function can extend with our properties. Okay? On the other hand, if you have an extension on an eta minus 1 domain, then its EH must be at most eta. That's because of the Fabian inverse. So there's a converse to this, right? And this is really important in what we want to do. Let's see. Well, I can keep the suspense up, or we can talk about it for 2 more minutes. Right? So that means, for example, right, if I have an infinitely increasing term with a certain exponential height, I get a bound on the exponential height of its compositional inverse. So then, not a precise bound, of course, and compute it exactly. Infinitely increasing, if beta is the maximum, F, see, that's the thing that I need for the theorem. Okay, and then. Then EH of F inverse, well, we know it's at least minus lambda, right? Because the level of F inverse is minus the level of F, so minus lambda. And the EH of F inverse must be greater than or equal to that. But it can be no more than eta minus lambda. Can't be too bad. And that's just because if I apply this extension theorem there, right, I have this map of angular level lambda extending on an eta minus 1 domain with image an eta minus lambda minus 1 domain. So its compositional inverse already extends to an eta minus lambda minus 1 domain with images exactly in half length. So according to this composition here, its EH can't be more than eta minus lambda. Yes. Okay. All right, and I will take this next time about for our purposes. Right? We'll look at these compositions of F with G inverse again. I'll get something about that too for monomials. Transfer. Do that